Okay, so today's topic is graphing function combinations. And your instructional objective is that you will be successful when you can find the sum, difference, product, or quotient of functions graphically, something new. And you can identify the domain. And the reason that I want to talk about this is because I believe it's really important for you to understand why the domain is what it is. Because I'm noticing that when we do everything with algebra, that when you're looking at the domain, it's really an abstract thing. And if you don't understand abstract thinking, you struggle. So let's start with some vocabulary really quick. We're going to talk about functions today. So we're just going to redefine functions. This is certainly not the first time you've seen this term. What is a function? A function is a noun. And a function is a set of ordered pairs where each x, or in other words, input, has exactly one y or output. We know this. We've discussed this multiple times just this year already. It will pass the vertical line test. So that's our first term. We're dealing with functions. We're working on operations and functions today. The other term that I want to remind you of is the term domain. Domain is also a noun. And domain has a lot to do with functions. Domain is the set of all x's. So we're talking about a function where you have a set of x's and y's where each x has a y. And then the domain is just what are the x's. We're not going to talk about the range today. Okay. So today what we're going to be doing is we're going to be adding and subtracting these things graphically. So let's talk about the criteria. The criteria is this. If, number one, f and g are functions, and number two, x is in the domain of both f and g, then I can add the functions, I can subtract them, I can multiply them, and I can divide them. And do me a little favor, put a little multiplication symbol in there. I don't know where it went. Okay, so here's what I'd like you to do over in the left-hand side of your note page. Over here, we're going to color code. All of my functions f will be in green. Switching to red, all of my g functions will be red. And all of my combo functions will be blue. If I add them, I will graph in blue. If I subtract them, if I perform an operation on two functions, I will graph the result in blue. So those are my color coding for today. So let's go and look at our conditions again. If these two conditions exist, then here's what I can say. I'm going to pick up my green pen. I can distribute and separate my f of x from my g of x. And I'm going to go ahead and distribute all of these real quick. So first I'm going to do my green pen so that I don't have to go back and forth between red and green. But I can take these combination problems and separate them. Then I'll go ahead and drop my green pen, pick up my red pen, and now I'm distributing. So here I'm going to be adding plus g of x, or subtracting minus g of x, or multiplying times g of x, or dividing over g of x, as long as g of x does not equal 0. So remember that. Denominators have restrictions. Okay? Now, here's the most important thing for you to understand. Notice that I have separated these terms. this combo, I've separated it into two separate y's. What does f of x really stand for? Y. G of x stands for y. So if their x's are the same, then I can add their y's, or if their x's are the same, I can subtract their y's, etc. So their x's have to be in common. So over here in condition number 2, the combo domain must be the intersection of the domains of your f, and that's an and sign, g. I'll make it an and sign, and g. Only. They have to have the x's in common in order for you to add their y's or subtract their y's, etc. Okay, so here's what we're going to do first. I would like you to notice that my pictures are colored and yours are not. So get out your red and green pen and just quickly, what's up? Yes. Just quickly color code those two functions. Okay, over here, here's what we're going to do. In our first two examples, we're going to do addition and multiplication. And over here, I just want to point out that addition and multiplication are commutative. What does commutative mean? What's a commute? Isn't a commute like a traveling back and forth? Well, here's what this means. The f plus g of x is exactly the same as the g plus f of x. The two functions can commute, switch places with each other, basically, but it won't affect the result. And multiplication is that way too, right? The f times g of x is the same as the g times f of x. So when we're adding and subtracting functions on a graph, you don't have to be super careful about what's your starting function and then what are you adding or subtracting, because 1 plus 5 is the same as 5 plus 1, same thing, 1 times 5, 5 times 1. Okay, so we're going back over here to these graphs now, and I'm going to look at this first one here. Here's what we're going to do, blue pen. In this example, we are going to combine the f plus g of x. So we're going to graph their combination. But let's separate first. So I'm picking up my green pen. We are going to be adding the f of x, that's a y, remember, plus the g of x. Okay? And you're just going to have to watch my pen on the board because I can't go up to the board and point. So remember that I'm adding y's, but I can only add their y's where they share a domain. So let's look at our green function and our red function. Do they share the same domain completely? No, but they do overlap from where to where? From 0 to 3, right? So if I want to come over here and I want to add this green function to this red function, they have to share a -2 for x, but do they? No, where x is -2, I have f of x, but I don't have g of x, so I can't add anything. So my result isn't going to graph there. Pick up your blue pen. We're going to start where they share an x. They share an x at x equals 0. We are going to add their y's. Look here. Where am I? -2 plus -1 is -3. So we're adding them and we're plotting their addition. Let's go to the next set of points where they share in the domain. X equals 1. Green. What's my y? 0 plus is 3. And does it matter if I go 3 plus 0? No. All right. Going to my next set of points where x equals 2. They share x equals 2. That's -2 plus -1 is -3. Last set of points that they share where x equals 3. You're doing 0 plus 3 is 3. And then you know what you do? You just graph it. And hopefully you do a little bit better than me. It's hard to do when I can't see what I'm doing. And there you have it. You have added those two functions where they share a domain. So I'm hoping that the illustration that their domains have to be an intersection in order to add them. So let's identify the domain of our combined function. 0, 2, 3 closed. That's the only part of the two functions that I'm allowed to add because those are the only x's they have in common. All right, questions? Okay, then let's try this one. In this situation, we're going to do f times g of x combined, blue pen, switching. So that's the combination. We're going to separate the f of x times the g of x. Again, we can only, they're both functions for sure, pass the vertical line test, but I can only multiply them where they share domains. So I have to go here and look at, I'm doing green times red. Does it matter if I go red times green? No, multiplication's commutative. So let's do this. -2 times -1 is positive. Oh, red, blue pen combo. Okay, going to where x equals 1 for both of them, multiply 0 times 3. -2 times -1, 2. And 0 times 3, 0. And that's it. We can just graph those 4 points, and of course all their in-between points as well. And there you have it. You can multiply them where they share a domain. So what's the domain of this function? 0 to 3 closed. There it is. So when you're adding and subtracting, hopefully now this is becoming a little clearer. We're actually putting all of this algebra into practice. Okay, so not so bad when it's adding and subtracting. But let's go to the next set. Okay, so here we go. The line is green and the parabola is red. Take a moment to get those. Even if you just label it f of x green and label the parabola in red, g of x, and you don't actually color them, that's okay. But I think the color's helpful, especially when you're subtracting and dividing. So I would do that. I'll give you a moment. Okay. So off to the left-hand side, I'm going to say this. These are going to be my subtraction examples, and just remember, subtraction is not commutative. Subtraction is not commutative. F minus g of x does not equal g minus f of x. Unless they're both 0. That's not going to be true. So be really careful. We must be careful when we're doing our subtraction to make sure we know what function are we starting from, what function are we subtracting. Really, really crucial. Okay? Subtraction is not commutative. So here we go. We're going to do subtraction both times. This first one, we're going to do the combo f of x, f minus g of x. And this one over here, we're going to do the g minus f of x. So there's my blue. And then I'm going to just go ahead and mark both of them. So this one's going to be f of x, and then this one's minus f of x on this side. And then this is minus g of x, and this one's going to be g of x minus f of x. So there we have those. You might get ahead of me if you're really starting to get this, and that's okay. Let's start with this left-hand side picture. I'm grabbing up my blue pen. So I'm subtracting the G function from the F function. So I'm taking red away from green. So I'm looking where their domain overlaps. Can I start here where x equals -3? No. How about x equals -2? Yes. So yes, because they share both. They both have x equals -2 in the graph. Yes, right here. So we're doing green minus red. 4 minus 5 is -1. Now, notice that the green and red have switched. Green's above red now. So we're doing 3 minus 2 is 1. Green minus red. 2 minus 1 is 1. Now they switch spots again. 1 minus 2 is -1. And then the last one. Green minus red. 0 minus 5 is -5. Okay, so this is feeling like it's supposed to be a parabola, right? Yes, it should be, because I'm doing a line minus a parabola, so I'm going to get a parabola upside down probably. So I actually need to get this vertex right here. So here's what I'm going to do. I'm going to find out what is, where x is -1/2. What am I on my green? Where am I? 2.5. All right, here. Where am I on my red? Approximate. 1.25? Okay, so let's do 2 1/4 250 minus 125. 1.25. All right, so let's graph. Interesting. We got a section of a parabola, right? We did. What's our domain? We need where they share. -2, 2, 2. Done. And so there you go. You've subtracted a parabola from a line. Interesting that that parabola flipped over. Got a little bit of a shift in it. Well, let's go see what happens if we take the line away from the parabola. Okay, so you guys try it without me. Press pause if you're at home watching this video, and then play when you want to check your answer. And there you have your picture. Your domain is the same, -2 to 2. But you'll notice that when we compare the two to each other, their combinations are different because subtraction is not commutative. Okay. All right, on the back, we have 2 more to do. So your constant is green, and your negative slope is red. And we're going to do division operations here. So just remember that division is also not commutative. So the f of x over the g of x, that is not how I want to write that. Let me back that up. I erased it. I didn't mean to. Division is not commutative. The f over g of x does not equal the g over f of x. Okay, not commutative. So you shouldn't get the same result when you're doing these division problems. Also, make yourself a little note that your denominators cannot equal 0, that is a domain restriction, which means that it could create an asymptote. Vertical asymptotes. And I'm not going to ask you to do these on your own very much because I want to review how to graph rational functions before we do too much of this on our own. Okay, so here we're going to do the f divided by g of x And over here, we're going to do the g divided by f of x. So green, we're doing f of x over, and over here, we're putting the f of x in the denominator. So in this case, f of x cannot equal 0. But I don't think the f of x ever equals 0 in our picture, so we don't have to worry about that. And then we're going to do g of x over here. And remember that our g of x cannot equal 0. And I'm going to clean that up because that looks terrible. All right, so here we go. We've color-coded. I hear you all dropping pencils, doing all your good stuff. So here I have a constant function divided by another linear function. Let's see what happens. We have to look for where their domain overlaps. I've got my blue pen here. So can I divide where x equals -3? No, because they don't overlap in that domain. So let's start here where they do share -2. Here we go. Green divided by red. -1 divided by 3. That's -1/3. Okay, so -1/3 is right there. Okay, let's do this one. Next one over. -1 divided by 2. -1 divided by 2 is -1/2. Beautiful. Next one. -1 divided by 1. -1. I like it. See that curve starting to happen because it's a rational function. Here we go. Problem. -1 divided by 0. That is undefined. 0 cannot be under the line. That is undefined. So there's our asymptote. We are not allowed to graph there. So here's what I know about the left side of this function. It is doing this from here. And then it's going to curve and approach my asymptote, but it's not going to touch it. But it does go to forever -infinity. It'll just get closer and closer and closer to 1. Now let's switch to the other side. Here we have our green and our red are the same number. -1 divided by -1 is +1. And then green divided by red. -1 divided by -2 is +1/2. And that's it, because the green doesn't have any overlap of red, so we can't graph anymore. So this side of the function does that. So when we go to talk about our domain here, we're saying that our domain has a split in it from -2 approaching 1 union with non-inclusive 1 to not infinity. Come on now, frame. That does not go to infinity. It goes to 3, right? It's such a habit to write infinity. Okay, so you can see you got a rational function there. All right, let's see what happens when we do this one. So this one we're doing red divided by green. Picking up my blue pen. Here we go. 3 divided by -1. -3. Yeah. Let's keep going. 2 divided by -1. Okay. 1 divided by -1. -1. Okay. 0 divided by -1. 0. Yeah, that's not undefined. I can do that. -1 divided by -1. 1. And then -2 divided by -1. Wait, that's a line. What? Interesting. That's because we divided by a constant in the denominator. What's my domain? -2 to 3. No interruptions. Okay. So there we've added something to your toolbox. You now can add, subtract, multiply, and divide functions on a graph. But I do want to remind you of a couple things. Tonight in your assignment, you will be doing problems 1 through 6 on 3.1b. So I'm going to write that down here. 3.1b, 1 through 6, and that assignment is on Canvas. But you are having to graph the starter functions, the f of x and the g of x by yourself. on your own graph paper. So just some reminders. If you have to graph a radical function, remember your domain restrictions. Your B is your shift, yes? Okay, so remember that your domain restriction must be greater than or equal to 0. Okay, so this is your domain restriction. And I think we should quickly just graph the parent function of the radical function so that you can just take your radical function, plot your points, and then shift them and replot the points so that it goes a little bit faster. I didn't put really complicated graphs on your assignment. So let's just graph the parent function of the radical function and talk about the points that you graph when you graph f of x equals the square root of x. If there's no a, no stretches, no compressions, your pattern of points is always the same. What's my restriction on my x in this situation? Can't be negative. So what's the first x I can use? 0. 0. Square root of 0 is 0, right? Square root of 1 is? The next perfect square root is 4. The square root of 4 is? And then the next one is 9, etc. Okay, so when you're graphing radicals, pay attention to the pattern of points from your starting point. Rise 1, run 1, rise 1, run 3, rise 1, run 5, rise 1, run 7, etc. When you're graphing a radical and there's no stretch or compression, your points always follow that pattern. Okay. The other one that I want to talk to you about is the quadratic, because you will be graphing a few quadratics, but they'll be simple quadratics, no shifts or no horizontals. Okay, it might have a vertical stretch or a vertical shift, but nothing horizontal. Let's talk about the parent function here because I want to talk about its pattern of points as well. So do I have any domain restrictions? Okay, so where's my vertex on here if there's no shifts? 0, 0. All right, if x squared, so 1 squared is, and 2 squared is 4. And negative 1 squared is also, and negative 2 squared is also. Okay, I want you to compare these two because they're inverses. So this one graphs like, maybe it's going to let me graph like that. And of course, this one graphs like, yeah, it's half a parabola. It is. Look at your pattern of points on your parabola. From your vertex or your starting point, right 1, up 1, right 1, up 3, right 1, up 5, right 1, up, and then of course it's a mirror on the other side, up 1, up 3. Do you see the connection between those two functions? Learn to graph those patterns because you're going to graph a lot of radicals and a lot of parabolas, and it's just better if you know what their pattern of points is. Please remember, multiplication and addition commutative, subtraction and division not. 1 through 6.